Hello and welcome back. Today I want to continue talking about wideband transformer-based signal splitters by looking at the problem of odd output channel numbers and odd impedance ports. In other words, how do you make a splitter that has more than two outputs, namely 3? Now, the core design I will be working with today is based on the 0-degree splitter discussed in a previous video. So, just in a nutshell, when you want to build a two-output splitter, you can do this with a split-winding inductor that has an isolation resistor across its outputs. Here, the inductor is split exactly in the middle, and the isolation resistor has a value equal to twice the output impedance. And you also need an impedance matching transformer that adapts the input to the second transformer. So here, the turns ratio needs to follow this equation as closely as possible. So these are the main building blocks of a 0-degree signal splitter. So last time we looked at the use case where both the input and the output port all had the same impedance values, whether it's 50 or 75 or some other value. But that will not always be the case. So first, let's generalize this design a bit. Now, for the matching transformer, this is just a basic transformer. So the impedance ratio is equal to the turns ratio. This can be built for any impedance ratio you need. On the other hand, the splitter transformer, we have far more variables to look out for. So first, the isolation resistor needs to be equal to the sum of the outputs, and the input impedance is equal to the two outputs in parallel. But now we have an issue. The condition you need to make the isolation resistor work is to have the same phase but also the same amplitude at the two outputs. In other words, the output powers will be dependent on the output impedances. If these are different, then the output powers will also be different. If you wish to keep the benefit of isolation, this will be a limiting factor that needs to be accepted. Finally, regarding the turns ratio, this needs to be equal to the impedance ratio, no square roots involved. So we can quickly check this by building a setup with two different loads, one 50 and one 100. And therefore, the source needs to be 33 ohms, which is the value of the two loads in parallel. Now, if we run this circuit, we can see that the amplitude of the signal source is around 0 decibels, which is the half of the value of 2, so the source is matched to the load. And if we look at the two loads, we can see that both of them, after a certain point at least, have the exact same voltage value. But since the resistances are different, that means that the power levels are different. Now we can figure out the power level by simply plotting the voltage squared divided by the resistance, and this gives us a difference of 6 decibels, but it's easier to observe this if we plot on a linear scale, and we can see that one of our values is around 20 milliwatts, while the other is 10 milliwatts. In other words, the power on the larger resistor is half that of the smaller resistor. So, using these principles, you should be able to design a 0-degree splitter with any number of outputs and with any port impedance. So, to test things out, let's look at the problem of creating a three-way splitter. For this task, I found two main ways to do it. To make understanding this a bit easier, let's impose that all ports are the same impedance, say 50 ohms. So starting from the output, the easiest way to make a three-way splitter is to first combine two of the outputs into a single line. This will be half impedance, so 25 ohms, and then we need another transformer, but this time an imbalanced one. And the input of this will be 16.6 ohms. And to finish things off, we need an impedance matching transformer to go back up to 50. So this has all ports at 50 ohms. But are they the same power level? Well, if we look at the first splitter, the two output impedances are different, therefore the power here will be different, but inversely proportional to the impedance. 25 is half of 50, so the power on this line will be double. When this goes through the other splitter, then we get half at each side. So finally, all three ports do have the same power level. So this is an example of a splitter that provides output isolation, 0 degrees between the ports, and equal power splitting. So what I have here is a three-way TV splitter, one that was built properly. And this provides three isolated outputs using the principles that we've just discussed. So signal comes in through the bottom left port, goes into the first transformer, gets impedance matched, and then goes into the second transformer. Somehow both of these are built on the same core. But anyway, one side goes out, and the other goes into the third transformer, which again splits it into two, but this time into equal amounts. Other than the transformer and the isolation resistors, this design also contains DC blocking capacitors, one at each port, so these ceramic capacitors, as well as few more SMD capacitors needed to improve the bandwidth. Just to confirm the operation, I built a simplified version of the circuit in the simulator. So I skipped all of the capacitors and I used ideal transformers. And for the isolation resistors, on the top transformer I used double the output impedance, so 100 ohms. And for the middle transformer, I used the sum of the two interconnected impedances, so 75. Now, if we run the circuit, and we start by looking at the input side, again we see a value of 0 dB, so our signal source of value 2 is matched to the circuit, we see half of that value. And if we look at the various outputs, we can see that all three of them have exactly the same value, which, once it's stabilized, is at around minus 4.77 decibels, which is a third of the 0 decibels of input power. So the splitter is working as expected. Now, I did find a more complicated way of making such a splitter, but to some extent at least, it's a bit more symmetrical. I'm not sure if that's a good thing, but I tried building it anyway. So the second design to analyze today follows a similar logic, but rather than having the 1 to 2 splitter as the second stage, it's used at the output. So we have two transformers splitting the signal into 50 and 100 ohm loads, and then the two 100 ohm loads are put in parallel, giving us the desired 50. The two inputs are then combined, and a final impedance matching transformer is used. Now, with this design, what I meant by better symmetry is that the outputs all look very similar. The signal always goes through the same transformers, so you should get similar imperfections. That's the theory anyway. Now, for this circuit, you need 4 transformers and some resistors. As far as the isolation resistor values go, for the output transformers, you need 150 ohms, which is a standard value, so no issues here. But for the middle transformer, you need 66.66 ohms, which is not really standard. However, if you want to build this, you can still obtain this value by putting 100 and 200 ohms in parallel. Now, if we run the circuit just to check it, we can start with the input and see again that it hovers at around 0 dB, so the signal source is matched to the circuit. And if we look at the three outputs, like before, all three are at the same value, so after stabilization, and the value is minus 4.77. So the input power is equally split among the three outputs. So both this and the previous circuit should do the exact same thing, right? Well, to highlight the advantage of the more complicated circuit, what I have here is both circuits, but the difference compared to the previous simulations is that I put all the transformers to have a coupling factor of 99%. So previously all of them were at 100%. Now, you might have a better value in practice, but the idea is that with any real transformer, you can never get exactly 100%. It will always be something lower. Anyway, with this modification, if we rerun the setup, and we start with the complicated circuit and look at the three outputs. So first of all, there's a high frequency corner appearing, but other than that, all three outputs give the exact same amplitude value as well as the exact same phase shift value. But in contrast, if we check the simpler circuit, so the one with 3 transformers, the first 2 outputs have the same amplitude and the same phase, but the third output has a different amplitude and different phase at high frequency. Sure, it's the same at low frequency, but nevertheless, this sort of a behavior can become problematic in certain applications. If you just need a simple circuit, then this will be good enough. So for most applications, this will be sufficient. But if you have more stringent requirements, so you need exactly the same phase and amplitude under all frequency conditions, then the first circuit will be better. So this is the design I ended up building. I put all of the circuitry into a small metallic box with the input port on one side and all of the output ports on the other, and it turned out to be quite a nice little build. So the schematic that I ended up building is the following. I added a set of DC blocking capacitors on both the input and the outputs, so 100 nanofarads in all cases. And for the 4 transformers, I didn't really make any inductance calculations, I just tried to keep the correct turns ratios. So for the middle transformer, it's 1:1, so 2 times 11 turns. And for the output transformers, these are 2:1, so I used 9 and 18 turns, with the larger value being on the high impedance side, so the 100 ohm side. And for the input matching transformer, well, here, ideally, we would want a turns ratio of the square root of 3. But that's not gonna happen. So 2 very close values, which are used in practice, are on the one side 5 and 3, which give a ratio of 1.66. This was used in the TV signal splitter that I showed earlier, but a far better ratio can be obtained with 19 and 11. So this is much closer to the square root of 3. One side of the transformer has 11 turns, and the other has 8, so 19 minus 11. This ratio should give a far better result. Anyway, to finish things off, I also did in this extra capacitor, 180 picofarads, which for this particular build did seem to improve the high frequency bandwidth a bit. This is the build circuit. For the board, I used the basic perforated substrate. This circuit should mainly work for the HF band, so it's a bit more forgiving. And I used toroid cores for the free splitting transformers. This allowed me to make the windings nice and tight. So these are more or less one next to the other for better coupling. For the impedance matching transformer, it had a non-standard ratio of turns, so to try and improve coupling here, I just put it into a binocular core. And well, to finish it off, there are a bunch of capacitors and the isolation resistors. And well, that's about it. To test it out, there are 2 main tests I wanted to perform. So first off, check the insertion loss. How much signal passes through each port. So in an ideal world, the target would be 4.77 decibels, but I'm pretty sure it's going to be a bit worse. Anyway, I set up the VNA to insert signal on the input port and measured all 3 of the output ports, one at a time. But importantly, the unused ports were always terminated with 50 ohm terminations. Looking at the results, first we can see that even though I made 3 measurements, one on each port, they are almost identical. So any differences are very small. And regarding the actual values, well, it's lower than minus 4.8, so at 500 kHz, it's about minus 5 decibels, and then it increases to about minus 6.5 at 30 MHz, which is not perfect, but still a decent result. Now, the other test I wanted to perform was the isolation test. For this, I inject a signal on one of the output ports and measure another. Here, ideally, you should get very high negative values. So it's interesting to see what the actual behavior is. For this, I performed 3 tests. I measured from port 1 to 2, then from port 1 to 3, and finally from port 2 to 3. And while all the traces are more or less identical, but the values are less than stellar. At low frequency, the circuit is behaving as expected, so an isolation in the minus 30 dB range is pretty good, but as we increase frequency, the values start to become worse. finishing at around -15. So I guess there are a few things that should be tweaked to improve this build. Why can't this circuit be simple and just work? Now, just to check what was going on, I went back to the simulator. So for the isolation test, if we use ideal transformers and the resistor values that we've calculated, and we inject signal into the middle output port, and we check one of the other ones, we do see the ideal behavior. We see an ever-increasing amount of isolation. We get a similar story even if we swap the position of the signal source. So if we resimulate with the signal injected in one of the ends, and we check in the middle or at the other end, we see the same ever-increasing behavior. Now, if we move to the circuit with non-ideal coupling factors, so the 99% one, and we have the signal source on one of the end ports, and we check the outputs, well, we see the behavior that we've observed with our measurement. We see a dip followed by a decreasing amount of isolation. So the measurement was not wrong. Now, one interesting thing to observe is that if we increase the various isolation resistor values, so here I used about double for all three of them, and we recheck the isolation response, well, we get slightly better results. So our dip is attenuated. This is not a good thing, but the benefit that we see is in the high frequency range where attenuation is improved. So the exact best resistor value will in the end be dependent on the uncoupled amount of inductance, so I'm not sure what the ideal value would be, but the point is that if you use larger than ideal resistor values, you should get a more uniform isolation response. So after changing the isolation resistors and remeasuring, similar to what the simulator predicted, the overall results did become a bit more uniform. The minimum dip has disappeared, but the attenuation improved in the higher frequency range. I guess this is why in commercial splitters, the resistor values are higher than what you would expect them to be. For this circuit, these are still not the optimal resistor values, but rather something in between these, and the ideal ones are what's probably necessary. In the end, building a three-way transformer-based signal splitter is not all that complicated. But getting it to work well is another story. Anyway, based on the strictness of the design, you can have more or less complicated implementations. But as always, every project comes with its unique challenges. And with that said, hope you enjoyed this video, and if so, there are more similar videos on my channel that you might want to check out. And if you want to be up to date with my latest releases, also consider subscribing. See you next time. Bye bye.